Hi everyone. In this video, I'll be talking about a low-cost visual navigation system which you can use to navigate your robot indoors without the use of a GPS. This system is designed to be fairly simple and low cost and easy to use. So this presentation about AprilMAV will cover the basic features, operation, a few demos with a USB webcam, and then later on a real vehicle with ArduPilot, and then finally some hints and tips for using it. The name AprilMAV comes from the fact it uses April tags for its fiducial markers and MAV because it outputs in MAVLink format. So what is it? AprilMAV is an April tag-based indoor navigation system for robots. It uses visual cameras to look for April tags and use them as known positioning points, and then refers back to them as for its position. It is fully compatible with ArduPilot in that it will send out the necessary visual odometry feed and plug straight into ArduPilot. It's fairly low cost in that it will easily run on a Raspberry Pi 5. It can run on a Raspberry Pi 4 with lower end cameras. There's no position drift because the tags are fixed on the walls and so forth, and it's quite easy to set up. So why AprilMAV? Basically, if you're working indoors with a robot, for example, in a warehouse or a factory, it's very difficult / impossible to get an accurate enough GPS feed. There's other systems out there, such as Vicon, Ultra Wideband Beacons, UWB, or Visual Inertial Odometry, VIO. All three of those systems have their own disadvantages and advantages. Vicon is quite expensive to get the equipment. Ultra wideband beacons require active powered tags, and visual inertial odometry can require quite complex compute platforms. AprilTag is both inexpensive, doesn't require special tags or setup, and is quite easy to work on a low-end platform. So April tags. April tags are fiduciary markers similar to QR codes. Each April tag encodes the tag ID, and when a camera looks at the tag, it can figure out the position, the pose of the tag. That's the position and orientation relative to the camera. By knowing the position and orientation of a tag, the camera can then, when looking at the tag, it can determine the camera and hence the vehicle's position, and we can estimate the pose of the vehicle. So how AprilMAV works. First, we have the AprilMAV runs in a loop where first you've got the image capture, then the image rectification, where the image is converted to black and white if it needs, or grayscale if it needs to be, and any camera lens distortions are accounted for. Next, we detect any April tags in the image along with their position and orientations relative to the camera. If this is a tag we have seen before, i.e. it's in the tag database, we will get the delta between the tag's global position in the database and the tag's current position relative to the camera. And from over the course of 3 or 4 tags, we can then get a best fit pose. And then that's then sent to an EKF filter for filtering the velocity and position measurements. There's then converted into a MAVLink message and then sent off to ArduPilot. If a tag is detected that has not been seen before, that tag will be added to the tag database after being converted to a global position based upon the vehicle's current position. So April Mav is doing simultaneous localization and mapping of the tags, your standard sort of SLAM setup. Basic requirements for April Mav: you do need some sort of compute device, Raspberry Pi 4 or later, any sort of Jetson or x86 platform. April Mav is quite flexible in what it will run on. The key is choosing a good camera. You want a good machine vision camera with about more than 100 degrees field of view, so you can see lots of tags. Camera doesn't need to be color, and it does need to be able to capture at very low exposure time. So talking about less than 10 milliseconds exposure time. That reduces the effect of motion blur, which April Mav is quite sensitive to. For the April tags themselves, all you have to do is print them out on basically just on pieces of paper, usually A4 size. You can go bigger or smaller if you want. That's completely up to you. As long as the April tags are flat, you can just put them anywhere you want. Though you do want to arrange your tags such that the vehicle can see at least 3 to 4 tags at any one time. As an example, with a 2 megapixel camera with 110 degrees field of view, you can typically see a tag on an A4 size of paper. That's around a 20 by 20 centimeter tag. You should be able to get a detection range of 5 meters, give or take. Okay, now we are going to run through a few demos of the April Mav software and some of the common scripts contained within it. So first we will just source the Python virtual environment. For these demos, we are going to be using a Logitech C920 camera, which you can see in the camera.yaml file here. It's a fairly standard USB webcam, and I'll just be holding up an April tag in front of that. So first script is the process test -- camera equals Logitech C920, and that will capture a series of frames of the position and orientation of any April tags it can see. So if it'll just take a few seconds to start up. And there we go. It's taken 10 frames, and you can see it's found tag number 19, about 52.8 centimeters in front of the camera. That's along the z-axis. And it's capturing that at around 100 milliseconds per frame. So next script is the geotest. This builds on top of the process test by adding in the positioning and the EK filter determinations as well, which can be considered an all-up test of April Mav. So again, we're just going to run that with the tag in front of the camera. It's going to capture 20 frames, and you can see it's found the tag there, and it also gives some performance measurements of the various stages of the detection and camera. So this can be run in a GUI as well. If you want to see it run a bit more graphically. So -- GUI, we're also going to increase the number of frames it captures, 100 frames, just so we can see a few more things happening. So you can see I can move the tag there as it tracks it, and that changes the vehicle position. You can see there the Ford goes up and down. And we'll just close that. And finally, we just have April Mav itself, which builds upon geotest by adding in the necessary MAVLink connection to the vehicle. It's just AprilMAV.py, got the camera. Then we can just add which is the -- device. And this is just a standard Pi MAVLink connection string. So in this case, we're going to stream to port 14550, where our imaginary MAVLink connection is, and we can just run it like that. That will just take a few seconds to initialize. And you can see it running there. And every five seconds or so, it will give you a status update on the console. And here you see another demo just from the geotest script in AprilMAV. This is an all-up test with just a USB camera, an RGCam 497 model. Where on the left you can see that the tags being detected as I go around my living room, and then on the right you can see a plot of the vehicle's rotation and position over time. Lighting's not great here, so you can see the tags flicker in and out a bit. And on my laptop, this is running on my laptop, 5-year-old laptop, it's running at around between 60 and 80 milliseconds per frame. So call it maybe 15 frames per second. It is running a bit slowly, just because it is like a 4K camera, so it does have a lot of pixels to process. So here we have a quick demo of a robot using AprilMAV with the tags you see on the lower right, that it's detected on the ceiling of the room, and the robot's just following this marked course around the floor. The marked course is purely just to confirm the accuracy of AprilMAV. It's not using the floor markings to navigate in any way. So I've got the AprilMAV running on a Raspberry Pi 5 with a small RGCam camera on top. I've then got an ArduPilot-based flight controller as well. As you can see, the accuracy is about 5 centimeters or less. The robot's running at around 0.2 meters per second. And you can sometimes see when it turns, the motion below can sometimes make the tags disappear for a little bit until it regains their tracking. You can also see that even though I've got a light shining down from the ceiling there, that doesn't affect the ability to pick up the tags either. So now we're going to talk about some of the AprilMAV limitations. First one is tag visibility, in that AprilMAV needs to see minimum of 3 to 4 tags, preferably more at any given time. Next one is motion blur. AprilMAV is very sensitive to motion blur, as you can see on the picture on the right there. Any sort of motion blur means that AprilMAV will not be able to pick up the tag. Next is the trade-offs between resolution versus detection range versus frame rate per second. In that a higher resolution camera will give you a larger detection range, but that will then take longer to process on a per frame basis, so you get a lower frame rate. Therefore, you do need to balance your maximum detection range versus your desired frame rate, in that the desired frame rate should be preferably 20 frames per second. With some lower vehicles, you probably can get down to 10 frames per second. AprilMAV does need to see tags in its startup position, and the positioning system is always relative to where AprilMAV was started. So whenever AprilMAV starts up, that's its 000 position. Next, we're going to talk a bit about the advanced options. AprilMAV does have support for CUDA to speed up image rectification stage of the processing. Unfortunately, CUDA does not support the April tag detection algorithm, so you may find that running with CUDA, you will get less of a performance improvement than you maybe were expecting. April tags do have several tag families. For the most part, you'll want to use the 41H12 family. That's the default in ArduPilot. That does have the most stable pose detection. And there is also the EKF tuning. AprilMAV does have an EKF filter to help smooth out the velocities and position determination. By default, it works for around robots running at around 0.2 meters per second. You can change that with the p-val argument to the typical maximum velocity of the robot. Likewise with PXL, you can change that to the typical maximum acceleration of your vehicle. So, in conclusion, AprilMAV is a cheap and simple indoor navigation system for robots. It is not as accurate as other indoor navigation systems out there, but it is much cheaper and simpler to deal with. It works out of the box with common cameras and compute systems such as the Raspberry Pi and NVIDIA Jetsons, and it's designed to work quite easily with ArduPilot. AprilMAV is open source software published under the GPL license. I will leave a link to the GitHub repository for it below. Thank you for listening.